Okay, listen. So we are dealing with non-Newtonian flow. Come. I will try to tell the three non-Newtonian flows in one shot so that you won't get confused. First is plastic flow. What is the example of plastic flow? Flocculated suspensions. When you apply shear stress, when your shear stress is equal to yield value, the floccules will break. The floccules will break. What is yield value is? It is the shear stress required, force required to break the force of flocculation. Okay, it is the force required to break the force of flocculation. Then circulate okay, required to break the force of flocculation. See, we have floccules together like this. To break this, how much force is required? That force we call it as yield value. Okay, so this what the mechanism is. The mechanism is when you apply shear stress, okay, initially they won't move. Slowly, when it is equal to yield value, they will start move. Now they will behave as Newtonian flow. Important GPAT question. After yield value, plastic system will behave as Newtonian flow. Remember, this is the only system which behaves like that. Next, how to draw the graph? You are applying shear stress. There is no movement. That I want to indicate. So you are applying shear stress. Shear stress is there, but rate of shear is not there. So take shear stress here and rate of shear here. Shear stress is there, rate of shear is not there, means graph is starting from here. Remember, from here to here shear stress is there, but accordingly there is no rate of shear. So graph has to start from here. If you extrapolate this, this will touch at one point. This is called your yield value. Sir, what this graph is saying? Remember how to create the graph. I am applying shear stress, there is no movement. So I left the gap. Shear stress is there, no movement is there. So I left some graph. When my shear stress is about to equal to yield value, slowly particles will start moving apart. This moving apart is represented as curved line. Once it is equal to yield value, they will move as a Newtonian flow. Sir, how you are saying it is moving as a Newtonian flow? Straight line. This is called Rheogram. Another name for this is consistency curve. I forgot to tell yesterday. Remember this. Rheogram or consistency curve. Both are same. Rheogram or consistency curve. In the rheogram, if you are getting straight line, it indicates it is Newtonian flow. Okay, so here we get curved line, but this straight line indicates Newtonian flow. If you extrapolate this straight line, it will touch at some point. This point indicates this much shear stress you have required to make the system go to Newtonian flow. That what is your yield value. Okay, so how to create the equation? Mechanism, rheogram, equation. Equation is full force minus from here to here, half force divided by G is equal to U. U is plastic viscosity. Okay, U is plastic viscosity. This is your plastic flow. Then pseudoplastic flow. Okay, example for this is flocculated systems. Flocculated systems are example for this one. Example for pseudoplastic. Tell me, madam.
Pseudoplastic flow can be found in emulsion, suspensions, etc. In general, pseudoplastic flow is exhibited by polymer dispersion.
What are those polymers? Wait. Tragacanth in water. Write down. Example. Tragacanth in water. See, if a question comes, you should start with example, mechanism, rheogram, equation. Tragacanth in water, then
Sodium alginate in water.
Sodium alginate in water, then
Methyl cellulose in water.
Methyl cellulose in water, then
Sodium carboxy methyl cellulose in water.
sodium CMC in water. Any polymer in water will be your pseudoplastic system. Why the name is given pseudoplastic? We'll try to see. Listen, when you add polymer, see this is the liquid. In the liquid we have imaginary layers. When you add polymer in the liquid, this polymer will swell like this. And it will align between the layers. I said you, liquid has imaginary layers when it is flowing. When you add polymer in water, polymer will take up water and it will swell. Polymer will take up water and it will swell. It will swell as well as it will align between the layers. Now see, moving liquid is difficult. That is the reason when you add gum in water, it will become thick. This is the reason. This is thick. Then, when you apply shear stress, this polymer which is aligned between the layers, will be aligned in the direction of flow. Here, polymer will be like this. So polymer will be aligned in the direction of flow. Polymer will be aligned in the direction of flow. 1, 2. See the thickness. Whatever the water the polymer have took, it will leave the water. Whatever the water the polymer has took, it will leave the water. I will tell you the mechanism. Polymer means polysaccharide, sodium CMC, carboxy methyl group, cellulose. Cellulose will be like this. It's a sugar. Cellulose is a polysaccharide. Whatever your OH group is there, it will interact with water like this, with hydrogen bond. So your CMC, when you add to water, it will take up the water, it will swell, and also it will be aligned between the layers. Two restrictions to the flow. One, it swells, another it will align between the layers. Two restrictions to the flow. When I apply shear stress, whatever water it has took, it will give the water, and also it will align in the direction of flow. Due to this, what happens? This thick system will become thin. Thick system will become thin. Hence the name shear thinning system. When you apply shear, this system is becoming thin. Hence the name shear thinning system. So examples over, mechanism over, rheogram. I am applying shear stress, it is thinning. Okay, thinning means showing more rate of shear or less rate of shear. Good. So the graph will start from the origin and it will move upward. See, what it indicates is I am applying more force. From here to here I am applying force, but the movement is here to here. The force is less, the movement is more. So the graph will curve. Don't bad, because for a dilatant the graph is like this. Many students will do mistake if you bad. Don't bad. Understand the concept and draw the graph. The concept is I am applying less force. There is more movement. Shear thinning. How to represent that? See here like this. If you draw like this, what it indicates is force is only this much, but see movement is so much. So it will be going up. Next is it is represented by equation. N means exponent value. N means exponent value. If n is equal to 1, it is Newtonian flow. If n is greater than 1, it is non-Newtonian flow. Very important GPAT question. N is equal to 1, Newtonian flow. N is greater than 1, it indicates non-Newtonian flow. Next is I want to measure the value of n. I want to know the value. Sir, you just said it is 1 greater than 1. How will I come to know whether it is 1 or greater than 1? Apply log. Log x to the power of m. M log x is equal to log nu plus log g. I want to convert this into y is equal to mx plus c. Convert. What is y axis? So log g is equal to, convert. Log g is equal to, send it this side, n log f minus log nu y m x c. Draw the graph. Negative slope, so it is going like this, log g log f, and your slope is n value and intercept is log nu. This graph is not given in the textbook. Please write down. Graph is not given in the textbook. No forceful writing. If you are not writing, be quiet. No problem. Just listen. Anyhow, the video will be there. You can see there. రే ఇక్కడ కనిపిస్తున్నానా? ఇది నేను రాసేది కనిపిస్తుందో చెప్పు నాకు. Whose batch is today? Raise your hands. Chal. What we did is previous lab? Angle of repulse. Today we will do microscope. Okay. Next is dilatant flow. Dilatant flow. Example is, what are the example, madam?
Suspensions containing a high concentration of solids of small deflocculated particles. Suspension of starch in water. Inorganic pigments in water. Example, iodine.
Okay, listen. I will take one example. Example is concentrated suspensions. Means suspension where the dispersed system is more than 50%. The dispersed system is more than 50%. Means what? Water is less, solids are more. What do you mean by suspension? Water is more, solids are less. But in this case, concentrated suspension where water will be less, solids are more. That what is suspension in which the dispersion system is more than 50%. Suspension in which the dispersion system is more than 50% is the example for this. So how to represent that? We have suspension like this, deflocculated, and we have water covering the suspension. So there is only enough water to cover the suspension. Today's batch, remind me, I will show the proof how to walk on water. By using the dilatant system, you can walk on the water. How it is that? I'll make you to walk. Not you, your fingers will walk. Okay. So I can't take that much suspension here. I'll take in a beaker, I'll make it to walk on the water. Your finger will not dip in the water. I'll show you that. So in the water, there are more number of dispersed particles are there. And water is just enough. Water is just enough to fill the gap between the particles. Just enough. When you apply shear stress, there is no place for water or particles to go because they are full jam pack. Due to this, there will be creation of voids wherever I am rubbing. That is your voids. We call it as a void space. Means nothing. Because you are applying force, there is no place to go. There will be void space created. It has nothing there. This void will cause resistance to flow. So initially it is thin. Now after applying shear stress, it will become thick. Hence the name is shear thickening system. This system will become thick when you apply shear. Hence the name is shear thickening system. Okay, how to represent this in the graph? I am applying more force, there is less movement. I am applying more force, there is less movement. You can play boxing with the water, You can beat the water. Water will not make your hand to go inside. It will resist. It will bear as a hard rock. When you touch that slurry, the slurry will make your hands to go inside. When you touch it slowly. If you touch it very fast, it will be as a rock. Okay, it will be as a rock. Remind me, I will show you today in the lab. Okay, and successive batch also remind me, I will show you that. That what is your shear thickening system. Okay, equation is same equation. You need to write n is greater than 1, non-Newtonian flow. Shear thickening system. This what is your Newtonian flow. This is what your non-Newtonian flow. Okay, listen. I repeat once again. First listen, we'll see the difference. Plastic, the name is given pseudoplastic because see this curve is almost representing this curve, but it is not actually that curve. Hence it is pseudoplastic. Plastic, pseudoplastic and dilatant. Example here is flocculated system. There is deflocculated system. Remember this. Example here is flocculated. Dilatant is deflocculated. Here is polymers in water. Any gum in water. That is example. When you apply shear stress, the floccules will break. The force required to break the force of flocculation is called yield value. When you apply shear stress, initially it is thick. The polymers will apply the space between the liquid and also they absorb the liquid. It becomes so much thick, thick. Take gum. If you have any gum, take gum, try to rub it. It will become thin. There will be no gum. Your polymer is separated, water is separated. Okay. So when you apply the shear stress, best example for this is your evening snack samosa eating. Okay, how? You have sauce, you will do like this, it won't come. Next, it won't come. At one point your shear stress is so much that it will become full thin and it will come out in large quantity. Okay, or you need to squeeze it. Okay, you need to squeeze. Sauce is the example for shear thinning system. Initially sauce is thick. When you apply shear stress, it will become thin and it will come out. Okay. Next is dilatant flow. Example is starch in water or more than 50% dispersed phase in deflocculated suspension. When you apply shear stress in more than 50% deflocculated suspension, water is just enough to fill the gap between the particles. Water is less, particles are more. That's what it is, more than 50%. Water is 40%, particles are 60%. When you apply shear stress, no place to go. Due to this, void is created. Due to this, void is created. So what I am trying to say is, if I am separating these two people, air will be there between them. Okay, if it is deep, dilated flow, if I separate them, nothing will be there, void. This void will cause resistance to flow. Due to this, its thickness will increase. So initially it is thin, now it will become thick. Best example, you are in home, somebody is getting gun and shooting everybody. You want to prepare a bulletproof jacket. The best thing is custard powder. Take custard powder, add in a polythene bag, add only less water. Okay, if he shoots also, the custard powder will stop the gun, so stop the bullet. That experiment I will show you here. I will not shoot, I will show you that experiment. Okay, that is the example for this one. So here it example is sauce, here example is custard powder, here example is flocculated. Remember, flocculated plastic flow, deflocculated dilatant flow. See the graphs. Here this curved line indicates breaking of particle. After breaking, there will be as Newtonian flow. Among all non-Newtonian liquids, plastic flow is the only flow which after some time behaves as Newtonian. None of them will behave as Newtonian. Okay, so this graph is like this because we have less shear stress, more rate of shear. This graph is like this, more shear stress, less rate of shear. Please write down this. If over, we'll move on to next part. Okay, yesterday I missed some part. What are the different types of viscosity? I'll just tell you that, write on that one. Different types of viscosities. Yes. Intrinsic viscosity. First one is coefficient of viscosity. I already told you that. What is coefficient of viscosity? Next is intrinsic viscosity. So the name is given intrinsic because due to presence of internal thing, the viscosity is shown. To water you have added gum. Due to presence of gum, the viscosity is shown. So viscosity due to added substance is called intrinsic viscosity. It is used to measure molecular weight. Viscosity due to added substance is called intrinsic viscosity. It is used to measure molecular weight. Okay, relative viscosity. Viscosity of relatives. Don't write viscosity of relatives. What is relative viscosity? Relate means what? What do you mean by relate? Relate your marks with others. What do you mean by that? Compare. So compare the viscosity. Viscosity of a dispersion system divided by viscosity of a liquid. Write down relative viscosity. Viscosity of dispersion. This is viscosity of dispersion divided by viscosity of solvent. Viscosity of dispersion divided by viscosity of solvent. You got what we are doing? Listen, what I am trying to say is you have solvent, measure solvent viscosity. This is your solvent viscosity. In this solvent, you are adding some dispersion system, something you are adding. Due to this, viscosity may be decrease or increase. How much is the ratio? What is the ratio of added thing to the plain thing? So that's what this is. Added thing to the plain thing. Okay. What is the ratio for added thing to the plain thing? Is called your relative viscosity. You are relating the viscosity with plain water and added something added in the water. Specific viscosity. Okay, listen. Now for this, I have plain water. I have added some gum here. This gum increases the viscosity. How much increase in viscosity? I need to tell in the ratio. How will you tell that? Viscosity, specific viscosity means viscosity of a dispersion minus viscosity of a liquid divided by viscosity of a liquid. See here, dispersion minus liquid. Initially water viscosity is 10. After adding it is 15. What is the difference? 5. So how much increase here is 5 divided by your solvent viscosity is called specific viscosity, represented by SP. Specific viscosity. Next, reduced viscosity. Reduced viscosity. Specific viscosity by concentration. Specific viscosity by concentration. Next, kinematic viscosity. Viscosity by density. These all are important for your GPAT. Okay, are 2 marks questions also. Viscosity by density. Okay, reason. What is the units for viscosity? One scientist name is given. Good. Poise. Poise are centipoise. Units for kinematic viscosity is Stokes or centistokes. Remember, don't confuse. Units for kinematic viscosity is Stokes or centistokes. If you heard Stokes, it is kinematic viscosity. If you heard Poise, it is coefficient of viscosity. So how many are there? Coefficient of viscosity, relative viscosity, specific viscosity, reduced viscosity, kinematic viscosity. How many are there total? 1, 2, 3, 4, 5, 6. Ella? I forgot. Okay. Intrinsic viscosity. Okay. Factors influencing viscosity. So first factor is intrinsic factor. We have two factors, internally and externally. Intrinsic and extrinsic. We see about intrinsic factor. Can you guess? Good. Added substance. Okay. Molecular weight of added substance. Molecular weight increases, viscosity increases. Molecular weight increases, viscosity increases. Next, that added substance structure. If it is spherical, less viscosity, irregular, more viscosity. Structure and shape of added substance. Spherical, less viscosity, irregular, more viscosity. Interaction with solvent. Interaction with solvent. Now tell me, if it interacts, it is more viscosity, or doesn't interact, it is more viscosity? Interaction will. Example is your pseudoplastic. Pseudoplastic is interacting with water. Gum is interacting with water. Due to this, viscosity is more. Right on? Interaction, more viscosity. Extrinsic factors. What are the extrinsic factors? Good. Pressure. Application of pressure. Pressure increases, cohesive force increases, viscosity increases. Pressure increases, cohesive force increases, viscosity increases. Next, what about addition of non-electrolytes? Non-electrolyte is gum. Gum is a non-electrolyte. What happens if you add gum? Write down. Addition of non-electrolytes like sucrose, glycerin, alcohol will slightly increase the viscosity. Sucrose, glycerin and alcohol. Addition of electrolytes will decrease the viscosity. Remember this. Addition of electrolytes will decrease the viscosity. What about temperature? Temperature increases, viscosity inverse. Temperature increases, viscosity decreases. So intrinsic, extrinsic factors over. Next factor is shear time. You tell me this. If you are shearing for more time, viscosity increase or decrease? Depending on what you are taking, but most of the case it is decreasing. If you are taking dilatant flow, it will increase, but generally for plastic and pseudoplastic it is decreasing. This is your time independent rheology. Plastic, pseudoplastic and dilatant is your time independent. Sir, ask me, sir, why time independent? I am applying shear stress only for less time. I am applying what? I am applying shear stress for only less time. Hence we call it as time independent rheology. Next is time dependent rheology. After applying shear stress, if you leave it aside, what happens? After applying shear stress, If you leave it aside, what happens? Did I tell you opposite? No, write down that. Time independent is plastic, pseudoplastic, and dilated. Because we are applying only for less period of time. Shear stress is applied only for less period of time. After applying, we'll leave the system and we'll observe. Listen here. Why I am saying that dependent independent? See, I'll take a beaker. I'll apply shear stress. How much time? 2, 3, 5 seconds, 10 seconds. Over. This is time independent. After applying, I will observe what is happening. Whatever you observe, how it is behaving. It takes time. It takes so much time for the system to recover. Hence, it is called as time dependent. Previous one is time independent. Time dependent, I'll finish thixotropy and I will stop. Okay. Time dependent, we have thixotropy. Very, very important to develop a injection. First, I will tell you the definition. I will try to remember if I remember or not. Just give me start. Okay.